Welcome to WikiPodcast.
Hello.
Ever wonder what really makes everything tick? What lies beneath it all?
That's a great question.
Today we're doing a deep dive into what is physics, the language of reality.
Yeah, and our mission really is to get beyond just a simple definition. We want to understand what physics truly is.
How it gives us this unique way of looking at the universe, maybe compared to other sciences.
Exactly. And why it's so fundamental, why it's like the bedrock for everything else we understand.
It's kind of mind-blowing when you think about it. The same basic rules apply to an apple falling from a tree.
And whole galaxies swirling out there millions of light years away.
Precisely. Physics somehow ties all that vastness and all that smallness together.
It really does. You should think of physics less like a school subject,
Okay.
and more like the actual vocabulary the universe uses to write its own story. Understanding physics is, well, it's like learning to read that fundamental language.
Okay, I like that analogy. So, if we're learning this language, where do we start? What's the core idea, the definition?
Well, in essence, physics is the scientific study of matter.
Okay.
What it's made of, its fundamental bits, and then how it moves, how it behaves through space and time.
Right.
And along with that, the related concepts of energy and force. It's really about uncovering the basic operating manual for reality, if you like.
So you said fundamental. It sounds like it's about as fundamental as science gets.
Oh, absolutely.
Yeah.
It's definitely one of the most fundamental scientific disciplines. I mean, think about it.
Okay.
When a chemist is studying how molecules bond, or maybe a paleontologist figures out how dinosaurs moved, or even a climatologist looking at weather patterns, they're all using physics principles, whether they explicitly state it or not.
That makes sense. It's sort of the underlying rules they have to work within.
Exactly. And it's not just other scientists, right? Our whole world, the technology we use every day.
Yeah, I was thinking about that. Like my phone.
Your phone, the TV, spacecraft, bridges, even something simple, like a mousetrap.
Right.
The design, how it works, it's all based on understanding physical principles. Physics is the invisible scaffolding holding up all engineering and tech.
And this understanding, it doesn't just come out of nowhere, does it? It's based on seeing things.
Precisely. At its heart, physics is an experimental science. It really starts with just looking carefully at the world around us.
Observing
Natural phenomena. Physicists look for patterns, things that happen over and over again in the same way.
And those patterns lead to the laws.
They lead to understanding, yeah. We build our models and theories based on those observed patterns. It's a constant back and forth between watching and explaining.
Which really shows why getting a grip on basic physics can be such a powerful tool. It helps you understand so many other things kind of quickly.
It really does give you a framework.
Now, the word itself, physics, it has history, doesn't it?
It does, yeah. It comes from the ancient Greek word physika. Yep.
Which basically meant knowledge of nature, or the study of natural things. And that came from physis, which just means nature.
So way back then, it covered pretty much everything about the natural world.
Pretty much. Historically, what we call physics today was all wrapped up in a broader field called natural philosophy.
Ah.
That included trying to understand what matter was, what life was, how the stars moved, things we now call chemistry, biology, astronomy. It was all one big inquiry.
So what happened? Why did they split apart?
The big change was the scientific revolution. That really kicked off in the 17th century.
Okay.
It was a huge shift in how people investigated nature. Much more emphasis on doing controlled experiments, measuring things precisely, using mathematics to describe things.
Getting quantitative.
Exactly. And that more rigorous approach meant different areas started to specialize, developing their own tools and focusing on specific questions. That's how the distinct sciences emerged.
But they still connect, right? You hear about things like biophysics or quantum chemistry. Oh, absolutely. The boundaries aren't completely hard walls. Physics constantly intersects with other fields. Biophysics uses physics tools to understand biological systems, like how molecules fold or nerves transmit signals.
I see.
And quantum chemistry applies quantum mechanics, a core part of modern physics, to understand chemical bonds and reactions. These fields really highlight how fundamental physics still is.
So a breakthrough in physics could potentially ripple out and change things in biology or chemistry.
Definitely. When physicists uncover a new fundamental principle, it often explains things that other scientists were puzzled by.
Right.
And it can also spark totally new research directions, not just in science, but even in maths or philosophy. It's all quite interconnected.
Okay, so we've got a feel for what physics is now and how it kind of branched off. Can we walk through some of the big moments in its history. How did we get here?
Sure. If we go way, way back, you've got ancient civilizations, Sumerians, Egyptians, Indus Valley folks. They were looking up at the sky.
Astronomy.
Yeah, early astronomy. They were amazing observers, tracking the stars and planets, figuring out cycles, predicting seasons. It was practical knowledge, but also a basic awareness of celestial mechanics. That laid some groundwork.
So observation was key right from the start.
Absolutely. Then you get to ancient Greece and the pre-Socratic philosophers, people like Thales. They started doing something really radical for the time.
What was that?
They started rejecting supernatural explanations for things. They said, no, there must be natural causes. And they tried to use reason and observation to figure them out. Think about atomism, the idea that everything's made of tiny, indivisible bits. That came from them.
Wow, that's incredibly early for that kind of idea. It really taps into that basic human need to know why.
It does. Fast forward a bit, you get Aristotle in the 4th century BC. His book, Physics, was hugely influential for, centuries.
Right.
He had this whole system based on 4 elements: earth, air, fire, water, and things having natural places they wanted to return to. He argued, for instance, that heavier things fall faster.
Which sounds intuitive, maybe.
It does, but it turns out not to be quite right when you test it carefully. His system was comprehensive, but it wasn't really based on experiments the way we think of them now.
Okay, so influential, but eventually superseded. What happened next? Through the Middle Ages.
Well, things slowed down a bit in Western Europe after the Roman Empire, but scholarship continued in the Byzantine Empire. And critically, you had the Islamic Golden Age.
Ah, yes.
Scholars there inherited Greek knowledge, including Aristotle, but they didn't just preserve it. They built on it significantly. They really emphasized observation and logical reasoning.
Any key figures?
A huge one is Ibn al-Haytham, sometimes known as Alhazen in the West. He did groundbreaking work on optics and vision. He actually used experiments, like with pinhole cameras, the camera obscura, to test his ideas. He's considered one of the pioneers of the scientific method.
That's fascinating. It shows how knowledge moves and builds across culture.
Totally. And then comes the big one, the scientific revolution we mentioned earlier.
Right, 17th century.
Physics really becomes its own distinct science. Experimental, quantitative. You have these giants. Copernicus saying the Earth goes around the sun.
Huge shift.
Kepler figuring out the mathematical laws for how planets move. Galileo using the telescope to see things nobody had seen before, moons around Jupiter, phases of Venus.
Amazing.
And then, of course, Isaac Newton. Laws of motion, universal gravitation, calculus. He basically provided the mathematical language and the core principles for what we now call classical physics. The game totally changed. Theories had to be testable.
A real foundation was laid. What about the 19th century, Industrial Revolution time?
Exactly. That century saw massive progress, often linked to technology. Big breakthroughs in thermodynamics, the science of heat and energy, crucial for steam engines.
Jesus.
Also huge advances in chemistry and, very importantly, electromagnetism, understanding the link between electricity and magnetism, thanks to people like Faraday and Maxwell. This all solidified classical physics.
But there were hints it wasn't the full story.
There were little experimental puzzles that classical physics couldn't quite explain. Like, everyone assumed light waves traveled through some medium called the luminiferous ether, but experiments failed to detect it. And there was this problem with black body radiation, how hot objects glow. Classical physics predicted something absurd, the ultraviolet catastrophe. These were cracks appearing.
Cracks that led to the next revolution, I guess, the 20th century.
Precisely. The 20th century ushered in modern physics. It started right at the beginning, around 1900, with Max Planck. To solve that black body problem, he proposed that energy isn't continuous, but comes in little packets, quanta.
The birth of quantum theory.
Exactly. And then just a few years later, Albert Einstein comes along. 1905, his miracle year, he publishes papers on the photoelectric effect, using Planck's quantum idea, Brownian motion, and, importantly, special relativity.
Special relativity dealing with the speed of light.
Yeah, it addressed that constant speed of light problem and fundamentally changed our ideas about space and time being absolute.
Yeah.
Later, he developed general relativity, our modern theory of gravity.
Wow. So quantum mechanics and relativity, those are the pillars of modern physics.
They are. And the 20th century also saw the development of nuclear physics, particle physics, and eventually the Standard Model, our current, incredibly successful theory of fundamental particles and forces. It just shows physics never stands still. It keeps digging deeper.
It really is like peeling layers off an onion, finding more complexity underneath. So if we look at the toolkit physicists use today, What are the core theories?
Right, the essentials. Every physicist works with these fundamental frameworks. You've got classical mechanics, Newton's laws and all that, good for everyday motion.
Okay.
Then quantum mechanics, absolutely crucial for the atomic and subatomic world. Thermodynamics and statistical mechanics, dealing with heat, energy, entropy, large numbers of particles.
Got it.
Electromagnetism, the theory of light, electricity, magnetism, and relativity, both special and general, for high speeds, gravity, and cosmology. That's the main set.
And we sort of touched on this. There's a divide between when you use classical physics and when you need the modern stuff.
Yeah, there is. Classical physics works brilliantly for things that are, relatively large and not moving near the speed of light. So planets, baseballs, cars, fluids.
Most everyday experiences.
Exactly. But when you get down to atoms and electrons, or you look at GPS satellites where speeds and gravity effects matter, or you study the early universe, then you absolutely need quantum mechanics and relativity. Modern physics kicks in for the extremes.
So classical theory covers a lot, though. What specific areas fall under that?
Oh yeah, it's vast. You've got mechanics itself, which breaks down into statics, things staying still, kinematics describing motion, dynamics, forces causing motion, fluid mechanics.
Right.
Then there's acoustics, sound, optics, light, thermodynamics, heat and energy transfer, and the whole field of electricity and magnetism as described by Maxwell's equations. It's a huge chunk of physics.
And modern physics takes us into these other realms, the very small or very extreme.
Exactly. Modern theory explores how matter and energy behave under extreme conditions, super high temperatures, densities, or at tiny scales like inside an atom or nucleus, or vast scales like the entire universe.
What are some key concepts there?
Well, things like the principle of least action, causality, cause and effect, the idea that energy and other properties are quantized, come in discrete units, the importance of symmetry in physical laws, and the weird probabilistic nature of quantum mechanics. It's a different way of thinking about reality.
It sounds like it. And underpinning all this theory building and testing is the scientific method, right?
Absolutely fundamental. It's the engine of physics. You start with an idea, a hypothesis. You use it to make a prediction.
Testable prediction.
Crucially, yes. Then you design and run an experiment or make observations to see if the prediction holds up.
Yeah.
You compare the results. If they match, great. The theory gets stronger. If not,
Back to the drawing board.
exactly. You revise the theory or maybe discard it. It's this constant cycle, this dialogue between theory and experiment that drives progress.
And when a principle seems to hold up really well across many tests, we call it a scientific law.
That's generally right. Laws are usually concise descriptions, often mathematical, of fundamental relationships that seem universally true under certain conditions. Newton's law of gravity is a classic example. They summarize a huge amount of experimental evidence.
It sounds like you need both kinds of physicists, the
Wow.
theorists thinking up the ideas and the experimentalists testing them.
No, it's a vital partnership. Absolutely. Theorists build the mathematical models, explore the consequences. Experimentalists design clever ways to poke and prod nature, to measure things with incredible precision, sometimes finding things nobody expected.
And those unexpected results can send the theorists off in new directions.
That's often where the biggest breakthroughs happen. Theory inspires experiments, and surprising experimental results force us to rethink our theories. It's a really dynamic interplay.
So given all this, what's the ultimate goal? What is physics trying to do?
Broadly, physics aims to model the natural world with quantitative theories. It wants to explain the widest possible range of phenomena,
From the smallest to the biggest.
from quarks inside protons all the way up to clusters of galaxies and the universe itself. And a key goal is reductionism, in a sense trying to explain complex things in terms of simpler, more fundamental underlying principles.
Like finding the common roots.
Exactly. Think about how electricity and magnetism were once seen as separate forces. Physics showed they were two aspects of the same thing. Electromagnetism,
Ah, unification.
precisely. And then later, electromagnetism was unified with the weak nuclear force into the electroweak force. The ultimate dream for many physicists is finding a theory of everything.
Wow. A single theory for you.
Yeah, a single framework that could explain all the fundamental forces, all the fundamental particles, and maybe even why the universe has the properties it does. Why are the constants of nature what they are? That's the grand ambition.
That is incredibly ambitious. And you really can't talk physics without talking math, can you?
No way.
Right.
Mathematics is absolutely essential. It's the language physics speaks. It gives us the precision and the structure needed to describe the order we find in nature. Thinkers knew this way back. Pythagoras, Plato, Galileo, Newton, they all saw math as key.
So it's more than just doing calculations.
Oh, much more. Math is how we formulate the theories in the first place. It's how we organize the experimental data, how we derive specific, testable predictions from a general theory, and how we check if everything is logically consistent. The numbers, the equations, that's the bedrock.
There's kind of a philosophical difference between math and physics, though, isn't there?
There is. Physics aims to describe the real physical world. Its statements ultimately have to be tested against reality, against experiments. Mathematics, on the other hand, deals more with abstract patterns and logical structures. Mathematical truths follow from axioms. They don't necessarily need experimental proof in the same way. Physics makes synthetic statements about the world. Math often explores analytic truths within its own systems.
So physics uses math as its essential tool and language, but it's grounded in physical reality.
That's a good way to put it. Now, we often hear people talk about fundamental physics versus applied physics. What's the difference there?
Good question. Physics at its core is what we call a fundamental or basic science. Some even call it the fundamental science.
Because its laws underpin other sciences.
Excellent.
Exactly. Chemistry, astronomy, geology, biology. They all operate within the constraints set by the laws of physics. Fundamental physics research is driven primarily by the desire to understand the universe more deeply.
Curiosity-driven.
Pretty much. The goal is knowledge for its own sake, not necessarily a specific invention or product right away.
And applied physics.
Applied physics takes the knowledge gained from fundamental research and uses it to solve specific practical problems or develop new technologies.
Like building a better laser
Or developing MRI machines for medical diagnosis, creating new semiconductor materials for computers, designing more efficient solar cells. The focus is on a particular use or application.
And engineering must lean heavily on applied physics then.
Absolutely. Engineering is all about applying physical principles to design and build things. Statics for bridges, acoustics for concert halls, optics for cameras and telescopes, fluid dynamics for planes. It's physics put into practice everywhere.
Right.
And because the laws of physics seem to be universal, we can use them to simulate things, how a star forms, how a new airplane wing will behave before we actually build or observe them directly. It's incredibly powerful. And physics ideas even pop up in unexpected places, like econophysics or sociophysics, trying to model complex human systems.
It really does seem to be everywhere, underpinning so much. Okay, so if we were to wrap this up, what's the big takeaway? What is physics?
I think the key takeaway is that physics is our fundamental language for understanding reality. It's this dynamic, evolving quest based on observing nature, testing ideas through experiments, and using the power of mathematics to describe it all.
From the tiniest particles to the whole cosmos.
Exactly. It's our ongoing attempt to figure out the basic rules of the game, the fundamental principles that govern everything we see and everything we don't.
That's a really powerful way to think about it. It leaves you wondering, well, considering that immense scope, from the quantum foam to cosmic structures, what single question about the universe do you find most compelling right now, and why?
Ooh, that's a tough one.
Think about it. And for everyone listening, we'd love to hear your thoughts, too. Thanks for listening. Write us your opinion in the comments on what single question about the universe do you find most compelling and why. Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.